Hello, my name is Scott Smart. I'm a PhD student with the Mazziotti Group at the University of Chicago. Today I'll be talking about resolving correlated isomers of benzyne on a quantum computer with an error-mitigated quantum contracted eigenvalue solver. And so, just to give an overview, there's really three things I'd like to kind of talk about. First, why are we even interested in quantum computing for strongly correlated, molecular systems? And so we'll kind of give just a very simple answer as to why. Second, what is a quantum contracted eigenvalue solver? And then finally, what are some ways that we can actually use the current kind of noisy quantum devices that are available today for more than just very basic 1 or 2 qubit simulations? And so, just to start off, the electronic structure problem, which I'm sure we're all familiar with. Under the Born-Oppenheimer approximation, we can look at just the motion of the electrons and solve the electronic Hamiltonian. Under the time-independent Schrodinger equation, we can just look at these the eigenvectors here, and these can be used in materials design or looking at different chemical processes, maybe transition states, reactions, or we can look at more complicated electronic behavior or electronic transitions, and lots of interesting chemical phenomena. And so to approach this, classically we can look at wave function or reduced density matrix approaches. And so wave function approaches, generally we need to store the exact wave function or a large portion of the wave function to capture these strongly correlated phenomena, and so this can be quite costly. And so for RDM approaches, instead, we recognize that we can trace over all but 2 electrons, and so we only have to store the like the art of the fourth scaling to RDM. But we still have certain problems that can emerge. In particular, we have the N-representability problem, and then we also sometimes in certain schemes we can have a kind of a hierarchy of RDMs, which is where to get an accurate 2 RDM requires a 3 RDM, and to get a 3 RDM would require 4 RDM. 4 RDM require such and such and such until we eventually need the N RDM, which is just exponentially scaling as well. And so on a quantum computer, the main advantage is that we can actually simulate the wave function as a true quantum state. And so the quantum state hopefully can be prepared polynomially, but it has a this exponentially complex amount of information. And so, but really we don't want to get all the information. We only really need a subset of that information, and that's captured perfectly by the 2 RDM. And so this is why RDM approaches are really so appealing for quantum computing. And in general, with a lot of approaches, we'll see, you can see that there's just different ways for you to have an exponential sort of reduction in the cost in going from a classical to a quantum sort of calculation. But so we still, it's not quite that simple. So we do have to take care of how we're designing our wave function or our quantum algorithm. And so the first thing we might consider is the sort of theory that we're taking in. So if we use something like unitary coupled cluster, or a sort of heuristic approach where we just randomly parameterize the different excitations in the wave function, we need to see how efficient is our parameterization, how accurate is it, maybe even ideally with no noise. Are we maybe over parameterizing the wave function? How much classical versus quantum resources do we need? Is it too heavy on the classical? So on and so forth. But really we're more constrained by the capabilities of the quantum device. And so there's a number of limitations. This could range from how the device is connected and laid out, what's the quality of a particular C0 gate, or a correlated 2-qubit gate, how many measurements are we going to need to get a low enough statistical error, or how many circuits do we need in our tomography scheme. All these things are very important. So just to highlight some prominent methods, something like variational quantum eigensolvers, very flexible method. We can basically choose whatever ansatz we want, and we can kind of modify it in a number of different ways, and then we do a classical optimization over our parameterized ansatz. So one of the problems is that there can be a lot of local minima in the optimization, And also for a large number of parameters, doing this optimization could be kind of very costly. And we're maybe not even sure that we've reached a global minima in some instances. Either we've over or underrepresented the state potentially. So, and also, you know, on the positive, we can evaluate the energy. This only takes a 2 RDM, but there's not, you know, for instance, there's a number of schemes to measure the gradient of the kind of the different ansatz terms, and this can be there's some very elegant and simple techniques, and then there's just much more complicated techniques as well. So the contrast, if we look at something like quantum imaginary time evolution, you know, this is essentially a non-unitary operation, which we're finding a unitary projection of. And so in the worst case, this could be an in-body unitary transformation. And if we wanted to do a 2-body parameterization of it, even something like that requires a 4 RDM measurement, which, you know, could scale as r to the 8th with the number of spin orbitals. And again, we need a strong coherence requirement because we're going to have to evolve our state in imaginary time, and that can just take a large number of gates. And so the approach that we used and introduced is to use a quantum contracted eigensolver. And so first we're going to contract the Schrodinger equation under the 2-electron space, and we get the CSE, or the density equation, which requires the 4 RDM. And then we're just going to look at the anti-Hermitian component of it, which just takes the 3 RDM. And so the ACSE provides a sufficient but not necessary condition to have a wave function, but in general it provides a very good wave function, which can in principle be exact. And what the ACSE is giving us information on is kind of the invariance of the state with respect to arbitrary 2-body unitary transformations. And so this residual is going to be anti-Hermitian, which means that we can use it in an exponential operator to form a unitary transformation, which we can implement pretty easily on a quantum device. And so just to show the kind of quantum ACSE algorithm that we developed, first we would, you know, initialize some density matrix and wave function that we know, and then we can look at the residual, or this A matrix, which is just the ACSE, and then we can do this a variety of ways, either using a quantum computer and an auxiliary state, which requires a little more quantum resources but scales more favorably, or we can look at the classical solution using just the RDMs we get. And so we can either do this exactly with a 3 RDM from the quantum computer, or if we don't have a 3 RDM, we can use the 2 RDM and then reconstruct it. And again, actually, even if we use the 3 RDM, this approach has an advantage over the classical ACSE because our 3 RDM is exact. And so then we can evaluate the norm of the A matrix, and then if we want to continue, we'll basically use information from the A operator in constructing our new wave function, which then we can measure the 2 RDM. We can also look at the step size, maybe minimize the energy with respect to the step size, which is just a one-dimensional optimization, and then we iterate through. And basically, both these processes, getting the 2 RDM and getting this A matrix, have polynomial scaling, and so this can be a kind of efficient approach towards quantum simulation on a quantum computer. So, however, implementing it is not super easy. So, general quantum computing is very challenging. There's a lot of sort of problems that kind of emerge due to errors on the devices, and so we need to introduce some sort of error mitigation techniques. And here we're trying to use general techniques that we can apply to any size of problem. And so the first we'll just talk about is reducing the number of qubits, and this is basically by finding symmetries of the Hamiltonian, mapping them to qubits, and then because those qubits do not change in the simulation, we don't need to simulate them. So for instance, if we had a 2-2 active space, that Hamiltonian can be mapped to a single qubit. For 4-4, in our problem, this would be an 8-qubit simulation, and we can map this to a 3 or 4 qubit simulation. And so, as a kind of final error mitigation approaches, I'll just talk about sort of some of the problems with an iterative wave function. And so, ideally, if we took our step size and shrank it to 0, we would have that the difference between iterations would vanish, and so the n+1 iteration would be equal to the nth iteration. But unfortunately, on a quantum device, you can see here kind of these sample optimizations. At each step, we're adding a discrete number of gates, and so these gates, regardless of our step size or parameterization, are going to introduce a certain amount of error. And so if we just were to left this unchecked and just let the algorithm go ahead, we kind of get these resulting plots where maybe we are able to take 1 or 2 steps that lower the energy, but then we start to increase or stall out in our optimization. And this is just because noise on the quantum device has accumulated to the point where we can't lower the energy. And so to counteract this, we have a limit preserving correction, and we're going to just take this, this gamma sort of matrix where we take the difference between our prepared state with a 0 step size and our previous state. And so we know that this should be 0, but with noise it's not. And so using this, we can kind of preserve the continuity of our optimization across different iterations. And as you can see, it allows us to either continue our minimization or at the very least not worsen our minimization. However, we can potentially overcorrect here, and so we do need to utilize a sort of a purification scheme where we're constraining our 2-RDM to be positive semi-definite according to the D, Q, and G conditions. And so this is kind of a classical post-purification of our 2-RDMs. But in practice, we actually found it to work pretty well. So now getting to our application, benzyne, is an interesting molecule based on how we remove the hydrogens from the benzene molecule. We can have different isomers in the ortho, meta, or para configurations, and these have differing levels of electron correlation. And that the correlation we see is going to be driven by the overlap in these pi orbitals on the isolated carbons. And so these are used in benchmarking, and even though there's a lot of interesting single triplet gap things we can look at here, we're just going to look at kind of the ground state relative energies. And so moving on to our calculations, on the left you can see here we have our relative energies on the absolute energy scale, and just compared with different methods, we have the full CI for the 2,2 and the 4,4 active spaces, and then we also have our 3Q and 4Q representing our kind of best performing or fully error mitigated 3-qubit and 4-qubit runs. And so actually for our 3-qubit runs, we were able to obtain very accurate results. These are less than 2K cal per mole relative energies, and the absolute energies for the 3-qubit case were under 3K cal per mole. And so it's not quite the accuracy we'd expect, but for these systems it's still quite good. And so for the 4-qubit result, we have more gates that we're using, more qubits, so there is more error on the device, but actually our relative energies are still quite decent. They've just all kind of been shifted up by a certain factor. And on the right, we have a comparison of the different relative energies with the different error mitigation schemes. And really the most reliable happen to be our fully error mitigated schemes. And so also we can look at the natural orbital occupations. We want to look if we're getting a correlated 1-RDM, and really we can see that if we look at the full CI, like the 4,4 active space, for instance, the honolumos, really the paras, the almost biradical, and then the ortho and meta are more or less single reference kind of entities. And for the QACSE3 or the 3-qubit simulation, we really are able to capture the pretty good 1-RDM here. For the 4-RDM, the ortho configuration was a little under-correlated and the meta was over-correlated, but we still are able to see a distinction with the para isomer. And so just to kind of summarize the talk, the simulation of strongly correlated material does stand to benefit a lot from the advancement of quantum computing. And in this work, we use a contraction of the Schrodinger equation to kind of to find a solution to the ACSE, which scales favorably on a quantum device. And then with error mitigation, we're able to look at things beyond just 1 or 2 qubit simulations and to kind of isolate these differences in the correlation of these isomers. And so we're hopeful that these generalized approach can be used for larger and larger systems. And so we're hopeful towards applying these to other systems. And so just to give a thanks to David Mazziotti and also Nicholas Boyne, who worked with me on this work. And thank you all for your time.